Welcome! In this video, we'll be diving into the problem titled Palindrome Partitioning. This is a fascinating problem that challenges our understanding of recursion, backtracking, and string manipulation. We'll explore different approaches to solve this problem and break it down step by step. Let's get started. The problem we're solving is called palindrome partitioning. You're given a string S, and your task is to partition it in such a way that every substring in the partition is a palindrome. Once you've found all such valid partitions, you need to return them as a list of lists. Now, recall that a palindrome is a string that reads the same both forward and backward. For example, racecar and madam are palindromes, but hello is not. The input is a single string, which can have a length between 1 and 16, and it consists only of lowercase English letters. The output will be a list of lists, where each inner list contains one valid way to partition the string into palindromes. For example, if the input string is ob, the output would include two valid partitions, one where each character is its own substring, like b, and another where the first two characters form a palindrome, b. In the first case, and b are all individual palindromes. In the second case, AA is a palindrome, and so is b. Now, consider another input, like S equals a. Here, the string itself is the only possible palindrome partition, so the output is simply a. Another example is when the input is ABC. In this case, no substring longer than one character can form a palindrome, so the only valid partition is to treat each character as a separate substring. That gives us the output, a B, C. The constraints make this problem manageable. Since the length of the string is limited to 16, it's computationally feasible to explore all possible ways to partition the string. Additionally, the string contains only lowercase letters, which simplifies the process since we don't have to handle numbers, special characters, or uppercase letters. Now let's discuss some edge cases. First, if the input is a single character string like S equals a, the output is always a, because a single character is inherently a palindrome. Next, consider a string where all characters are identical, like AAA. Here, the output includes multiple partitions, separating each character individually, combining two characters into a palindrome, or even treating the entire string as one palindrome. Finally, if no substrings longer than one character can form a palindrome, like an S equals ABC, the output will simply have each character as its own partition. These examples highlight the variety of cases you need to account for when solving this problem. To solve the palindrome partitioning problem, we first consider the brute force approach. This method involves generating all possible partitions of the string and checking each partition to determine if all its substrings are palindromes. If a valid partition is found, we add it to our results. However, this approach is highly inefficient because the number of possible partitions grows exponentially with the length of the string. Checking each substring for a palindrome adds even more computational overhead, leading to a time complexity of O2 to the power of n asterisk n. The space complexity is O(n), due to the recursion stack used during partition generation. To improve upon this, we turn to an optimized backtracking approach. Here, instead of generating all partitions upfront, we incrementally build partitions while validating palindromes as we go. We use recursion to explore potential splits of the string. If the current substring is a palindrome, we add it to our partition path and recursively solve the remainder of the string. Once the recursion finishes, we backtrack by removing the last substring and trying other splits. This approach avoids generating unnecessary partitions and incorporates a helper function to efficiently check palindromes. The time complexity improves to O(n)(2 to the power of n, because we avoid redundant checks, and the space complexity remains O(n) for the recursion stack. An alternative strategy to backtracking is to use dynamic programming alongside backtracking. This involves pre-processing the string to create a DP table where DP, I, J, is true if the substring S, I, J plus 1, is a palindrome. With this table, we can validate palindromes during backtracking in O(1) time, further improving efficiency. The rest of the approach mirrors the optimized backtracking strategy, where we recursively partition the string using the pre-computed DP table for palindrome validation. The pre-processing step takes O(n)² time, and the backtracking process still requires O(n)(2 to the power of n, making the overall time complexity O n squared plus n times 2 to the power of n. However, the space complexity increases to O n squared due to the dp table, in addition to O n for the recursion stack. Considering these options, we chose the optimized backtracking approach as our primary strategy. This method balances simplicity and efficiency, avoiding the additional space overhead of the dp table while still achieving excellent performance. Moreover, the backtracking approach naturally aligns with the recursive nature of the problem, allowing us to prune invalid paths early and avoid redundant computations. Validating palindromes directly during recursion further streamlines the process without requiring pre-processing. This combination of efficiency and clarity makes backtracking a robust choice for this problem. When comparing strategies, we observe important trade-offs. The brute force approach, while conceptually simple, is computationally infeasible for large inputs due to its exponential growth in the number of partitions. In contrast, backtracking improves efficiency by pruning invalid paths early, exploring only partitions that have potential to be valid. The dynamic programming approach offers even faster palindrome validation with O1 checks during backtracking, but this comes at the cost of additional space complexity, which grows quadratically with the length of the string. Given the typical constraints of this problem, the space overhead of the dp table may not be justified. By focusing on the backtracking approach, we achieve a solution that is both efficient and straightforward to implement. This strategy avoids the excessive memory usage of dp while still leveraging recursive exploration to reduce the problem's complexity. Overall, backtracking represents a practical and elegant solution, striking the right balance between speed, memory usage, and implementation simplicity. The goal of this problem is to partition the input string such that every substring within a partition is a palindrome. A palindrome, as a reminder, reads the same backward as forward, like racecar or AA. To achieve this, we need to identify all possible ways to split the string into such valid partitions. For example, if the input is OB, the output should include partitions like A, B, and AA, B. To solve this efficiently, we use a backtracking approach. Backtracking allows us to explore all potential partitions, but with strategies to prune invalid paths early. The process involves iterating through all possible substrings of the input, checking if each is a palindrome, and recursively partitioning the rest of the string. A helper function, is_palindrome, ensures we can quickly verify palindromic substrings by comparing characters from the beginning and end of the substring inward. This lays the foundation for our solution. For example, the substring AA is a palindrome because the first character matches the last character. Similarly, for a longer string like racecar, we compare the first and last characters, then the second and second to last, and continue inward. Once we have the ability to check palindromes, we can implement the backtracking framework. The base case of our recursion occurs when the starting index reaches the end of the string, meaning we've successfully partitioned all characters into palindromic substrings. In this case, we save the current partition to our result list. For the recursive case, we iterate through all possible end indices of substrings starting from the current position. When we find a palindrome, we add it to the current partition and recursively process the remaining portion of the string. After exploring one path, we backtrack by removing the last added substring, allowing us to test alternative partitions. This approach is both systematic and efficient, as we skip over invalid substrings that are not palindromes. By pruning these paths early, we significantly reduce the number of recursive calls. The recursive depth is capped at the length of the string, and we maintain auxiliary data structures like a result list to store all valid partitions and a temporary list to track the current partition during recursion. To better understand this algorithm, let's walk through an example with the string OB. Initially, we start with an empty partition and generate substrings starting from the first character. Checking A, we find it's a palindrome, so we add it to the current partition and recursively partition the remaining substring OB. Next, we check AA, and since it's also a palindrome, we add it to the current partition and recurse on the remaining substring B. The substring OB, however, is not a palindrome, so we skip it. When processing OB, we first check A, which is valid, and then move to B, which is also a palindrome. At this point, we've reached the end of the string, so we add the current partition, B, to our result. Backtracking, we remove the last added substring and explore alternative partitions. The result list accumulates all valid combinations, such as AA, B, ensuring we've covered all possibilities. Analyzing the complexity, the time required arises from checking all substrings and making recursive calls for each partition. This leads to a time complexity of O, n asterisk 2 to the power of n, where 2 to the power of n represents the number of potential partitions. The space complexity includes both the recursion stack, which has a depth proportional to the string's length, and the result list, which stores all valid partitions. The Python implementation of this algorithm begins by defining the is_palindrome helper function, which checks if a substring is equal to its reverse. The main function partition includes the recursive backtracking logic. Starting from index 0, we iterate through all potential end indices, checking if the substring from start to end is a palindrome. If it is, we append it to the current partition and recursively call the function for the remaining string. When the base case is reached, meaning the starting index equals the length of the string, we append a copy of the current partition to the result list. Afterward, we backtrack by removing the last added substring to explore other partitions. The result list is initialized at the start of the function and returned at the end, containing all valid partitions. This implementation efficiently handles the recursive exploration and ensures that invalid substrings are skipped early, making it both elegant and effective for solving the problem. This implementation solves LeetCode problem number 131, Palindrome Partitioning, which requires finding all partitions of a string such that every substring in the partition is a palindrome. The solution uses a backtracking approach. First, we define a helper function is_palindrome to check if a given substring is a palindrome. This function uses Python slicing to reverse the string and compare it with the original. The main logic is implemented in the backtrack function. It takes two arguments, start, which represents the starting index of the current substring being considered, and path, which tracks the current list of substrings forming a valid partition. If start reaches the end of the string, it means a valid partition has been found, so we append a copy of path to the results list. Within the backtrack function, we iterate over all possible ending indices, end, starting from start. For each substring s, start in plus 1, we check if it is a palindrome using the is_palindrome helper. If it is, we add it to the current path and recursively call backtrack with the next starting index. After the recursive call, we backtrack by removing the last added substring to explore other possibilities. The results list stores all valid partitions, which is returned as the final output. The backtracking ensures that we explore all potential partitions while pruning invalid ones early. This solution has a time complexity of approximately O, n asterisk 2 to the power of n, where n is the length of the string. This is because there are 2 to the power of n potential subsets of substrings, and for each subset, we spend O, n, time to check palindromes and copy the path. The space complexity is also O, n, due to the recursion stack and path list storage. Here, we have the Java implementation of the palindrome partitioning problem. We start by defining the partition method, which takes a string s as input and returns a list of lists containing all possible palindrome partitions. To achieve this, we initialize a results list to store our final partitions and call the helper method backtrack. The backtrack method is designed to explore all potential partitions using recursion. It accepts the string s, a starting index, a temporary list path to store the current partition, and the results list to store the final valid partitions. The base case for this recursive function checks if the starting index has reached the end of the string. If so, it adds the current path as a valid partition to the results list. Then, we loop through the substring starting from the current start index to the end of the string. For each substring, we check if it is a palindrome. If it is, we add it to the path, recursively call backtrack with the updated index, and then backtrack by removing the last added substring from the path to explore other possibilities. To check if a substring is a palindrome, we use the isPalindrome helper method. This method takes a string str as input and uses two pointers, left and right, to traverse the string from both ends. While the left pointer is less than the right pointer, we compare the characters at these positions. If any pair of characters does not match, the method immediately returns false, indicating that the string is not a palindrome. Otherwise, the pointers move closer to the center of the string, and the comparison continues. If all pairs of characters match, the method returns true, confirming that the string is a palindrome. This function ensures that we only proceed with recursive calls in the backtrack method when a valid palindrome is detected, which is crucial for the correctness and efficiency of the overall solution. Here, we begin solving the problem with the input string ob. First, we initialize an empty list called results to store all the valid palindrome partitions. To start our backtracking process, we make the first call to the backtrack function with a starting index of 0 and an empty path. In this first call, we start iterating over the string from index 0, and we check the substring s, 0:1, which is a. Since it is a palindrome, determined by our is_palindrome function, we add it to the current path, making path equals a. Next, we make a recursive call to backtrack, advancing to the next index with backtrack 1, to continue exploring further partitions. In the second call to backtrack, we now start iterating from index 1. Here, we check the substring s, 1:2, which is another a. Again, the is_palindrome function confirms that it is a palindrome, so we add it to our current path, making path equals a. We then make another recursive call to backtrack with the updated path and index, calling backtrack 2 a. In this third call, we start iterating from index 2. The substring s, 2:3, is b, which is also a palindrome. Adding b to the path results in path equals b. At this point, we reach the end of the string, as the starting index becomes equal to the string's length. This means we've found a complete partition, so we add b to results. Afterward, we backtrack by removing the last element from the path, reverting it to so we can explore other potential partitions. By backtracking further, we return to the second call with path equals a. From here, we now check the substring s, 1:3, which is ub. However, ub is not a palindrome, so we skip it and continue exploring other possibilities. Eventually, we find another valid partition, path equals a, b, which we add to results. With no further substrings to explore, we've now completed the partitioning for the input ob. The final results for this example are b, a, b. Moving on to a new example, let's consider the input string racecar. As before, we initialize results as an empty list and make the first call to backtrack 0 to begin the process. For the string racecar, we systematically explore all possible palindromic substrings. Starting with single character substrings, we find that each character, such as r, c, and so on, is a palindrome. We also identify larger palindromes, such as racecar spanning the entire string and a sika within it. By combining these substrings in all possible ways, we generate valid partitions like r, c, e, c, r, a sika, r, and racecar. These partitions get added to results, giving us the final output r, c, e, c, r, a sika, r, racecar. Now, let's briefly look at a simpler example with the string AAA. In the case of AAA, we explore partitions of increasing size. Single character partitions, like are valid since each is a palindrome. Next, two character substrings, such as AA, also form palindromes, leading to partitions like AA. Finally, the entire string AAA is a palindrome itself, resulting in the partition AAA. The final results for this example are AA, AAA. The key takeaway here is how the backtracking approach systematically explores all possible substrings, using the is_palindrome function to ensure validity. By removing the last added substring during backtracking, we efficiently explore alternate paths, ensuring no possibilities are missed. To analyze the time complexity of the palindrome partitioning problem, we need to break it down into its key components. First, consider the process of generating all possible partitions of the string. For a string of length n, the backtracking algorithm explores all ways to place cuts between the characters. Each character can either have a cut after it or not, leading to 2 and 1 possible combinations of partitions. Next, for each partition generated, we need to check if the substrings within it are palindromes. Checking whether a substring is a palindrome involves comparing characters, which takes L time for a substring of length L. In the worst case, the string is partitioned into n substrings, and each palindrome check involves up to n operations. This means the total cost of palindrome checking across all recursive calls is n². Finally, the recursive backtracking process is represented by a tree with 2 to the power of n nodes, where each node involves work proportional to the substring length. These factors combine to determine the overall time complexity. Now, when we combine the factors discussed, the total time complexity of the problem becomes n*2 to the power of n. The 2 to the power of n term accounts for the number of partitions generated, while the n term accounts for the cost of performing palindrome checks. Turning to space complexity, the recursive nature of the backtracking algorithm means that the maximum depth of the recursion tree is n, corresponding to the scenario where the string is fully partitioned into single characters. This gives a recursion stack space of n. Additionally, the results list stores all valid partitions, which in the worst case includes 2n1 partitions, each containing up to n substrings. This results in n*2 to the power of n storage cost for the results. Temporary storage, such as the current path or substring being evaluated, requires n space during execution. Combining these, the overall space complexity is n*2 to the power of n, with the recursion stack and results storage being the dominant contributors. To put this into perspective, let's compare the optimized backtracking approach to a brute force method. A naive approach would generate all possible partitions, which involves 2 to the power of n combinations, and then independently verify if each substring is a palindrome. This leads to redundant computations for palindrome checks, as the same substrings are repeatedly verified. While the time complexity is still n*2 to the power of n, in the worst case, the lack of optimization makes the brute force approach much less efficient in practice. By contrast, the backtracking solution avoids this redundancy by directly slicing substrings during the recursion process. Further optimizations, such as using dynamic programming to pre-compute whether substrings are palindromic, can reduce the palindrome checking cost to 1 per query. This would improve the overall efficiency, though the time complexity remains dominated by the number of partitions at 2 to the power of n. In summary, the backtracking approach achieves n*2 to the power of n time and space complexities, balancing exponential growth in partitions with practical improvements in efficiency over brute force methods. When solving the palindrome partitioning problem, there are a few common mistakes that can trip you up. First, not handling edge cases like an empty string or a single character string is a frequent issue. For example, an empty string should simply return an empty list of partitions, while a single character string should return a list containing just that character as a single partition. Testing your code with these edge cases is key to avoiding errors. Another common mistake is inefficient palindrome checking. If you're repeatedly rechecking the same substrings, you're wasting valuable computation time. A good fix here is to use dynamic programming or memoization to store the results of palindrome checks, so you don't have to recompute them. Additionally, in backtracking, failing to prune the search space can lead to unnecessary recursive calls. You should terminate the recursion as soon as you encounter a non-palindromic substring. Lastly, an incorrect base case in the recursion can cause incomplete results. Always ensure that when you've processed the entire string, you return the current partition as part of the solution. These fixes can help you write cleaner and more efficient code. Another frequent source of errors is confusing the indices used for substring slicing. Off by one mistakes or using the wrong start and end indices can result in incorrect partitions. This is why it's crucial to carefully track the indices in your recursive calls and debug thoroughly when you notice any slicing issues. From an interview perspective, this problem is often used to evaluate your understanding of recursion and backtracking. Interviewers are looking for your ability to recognize patterns, such as when backtracking is the appropriate approach, as well as how you optimize the process. For example, they might ask about using memoization to minimize redundant calculations during palindrome checks. They also value candidates who can clearly communicate trade-offs between different approaches, like brute force versus optimized solutions that require extra space. Lastly, being proactive about discussing edge cases, like strings with all unique characters or just one character, can leave a strong impression, as it shows that you're thinking critically about the problem. This problem is closely related to several others that can deepen your understanding of similar concepts. For instance, LeetCode Problem 5, Longest Palindromic Substring, focuses on finding the longest palindrome within a string. Solving that problem can give you valuable insights into how to efficiently check for palindromes. Then, there's LeetCode problem 131, which is the very problem we're discussing, palindrome partitioning. This reinforces your skills in partitioning a string so that every substring is a palindrome. Another variation is LeetCode problem 132, where the challenge is to minimize the number of cuts needed to partition a string into palindromes. Finally, LeetCode problem 93, restore IP addresses, involves a similar backtracking approach but with the goal of generating valid partitions of a string based on specific constraints. Working through these related problems can help you build a stronger foundation and recognize patterns across different types of partitioning challenges. When approaching the palindrome partitioning problem, there are alternative strategies to consider beyond backtracking. One such approach is dynamic programming. Here, you can use a DP table to pre-compute whether substrings are palindromes, which helps reduce redundant checks during partitioning. The trade-off is that while this approach can significantly improve time complexity, it does require additional space to store the DP table. Another option is iterative backtracking using a stack. This involves simulating recursion with an explicit stack, which can sometimes make debugging and optimizing your solution more manageable. However, it tends to result in a more verbose implementation. Lastly, there's the brute force method, where you generate all possible partitions and check each one to see if all substrings are palindromes. While this is the simplest to implement, it has a major drawback in terms of efficiency, as it runs with exponential time complexity. Each of these approaches has its strengths and weaknesses, and understanding their trade-offs can help you choose the best solution for the specific problem or constraints you're working with. Great job working through this problem. To wrap up, we've summarized the key points and takeaways. Remember to practice backtracking and build your intuition for recursive problems. Thanks for tuning in, and be sure to like and subscribe for more problem-solving content. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!